Hi, my name is Junho Kim. In this video, I'll present our paper titled Calibrating Panoramic Depth Estimation for Practical Localization and Mapping. Given a single panorama image, panoramic depth estimation outputs a dense depth map from pre-trained neural networks. Since a full surround 3D map is obtainable from a single neural network inference, panoramic depth estimation can enable lightweight 3D map creation. However, the size of depth-annotated panoramic datasets are much lower than the smaller field of view counterparts. As a result, existing panoramic depth estimation methods fail to generalize in domain shifts that occur during deployment. We propose a calibration scheme to better adapt panoramic depth estimation networks during deployment. Given a network pre-trained on large number of panorama images, our calibration scheme aims to enhance its performance in new, unseen environments by training the network on a small number of test samples. To elaborate, during deployment, our calibration scheme employs test time training using loss functions that impose geometric consistency. The resulting calibrated network can produce more accurate 3D maps, which will be beneficial for downstream applications such as navigation. Now I will briefly explain the loss functions employed for our calibration scheme. The first set of loss functions, namely multi-view loss functions, operate by synthesizing panoramas at various random pose perturbations. Given the synthesized panoramas and their depth predictions, chamfer loss enforces the point cloud coordinates produced from the two depth maps to be similar, and normal loss additionally enforces the point cloud normals to be similar. Secondly, stretch loss imposes depth map consistency against stretched panoramas. To elaborate, we synthesize panoramas at various stretch rates and impose depth map consistencies against each stretched panorama. Due to the lightweight formulation of our calibration method, it can be easily applied on top of various localization and mapping tasks. Here I will showcase a sample application in the context of robot navigation. We consider a robot agent equipped with a 360-degree camera and an odometry sensor that outputs noisy measurements. While navigating the indoor environment, the agent creates a 2D local map using panoramic depth estimation and produces a global map by aggregating previously created local maps with pose estimation results. Under such a setup, our calibration scheme can be applied by first collecting training samples during navigation and using the samples for test time training the depth estimation network with the aforementioned loss functions. Now I will briefly share the quantitative results for depth estimation. We compare our calibration method against existing domain adaptation techniques. The chart on the left shows the mean absolute error, where each column corresponds to a domain shift displayed on the right. Our calibration method outperforms all the tested baselines, which indicates its effectiveness in adaptation. Now I will share some qualitative results on robot navigation. The figures display the occupancy grid maps generated from robot agents exploring an indoor environment with identical action sequences. The estimated grid map is displayed in blue. By applying our calibration method, robot agents can produce more accurate maps compared to the no adaptation case. In conclusion, we propose a calibration scheme for panoramic depth estimation to enhance generalization in new, unseen environments. Our calibration scheme operates by test time training depth estimation networks with training objectives that enforce geometric consistency. Experiments verify that our method can help generalization in diverse conditions and further improve mapping and localization performance in downstream tasks. Thanks for listening.